gauge and toric variety routes to entanglement.
Thanks very much for giving me the opportunity to present some stuff. Okay, about 2 years ago I was working at MIT thinking about chiral solitons and thinking about what that had to do with quantum phase transitions and topological transitions. And the office I got was in the middle of the string theory group. So I started finding out a lot, listening to a lot of talks on quiver gauge theory. Now, we've heard this morning a little bit about quotient groups. So this is a big thing for string theorists. It's been a big thing for string theorists for about 10 years. So the plan is, they have some Riemann sphere, they have some object which is some representation, say, some group of SU4. Quite a lot there. And what we want to think about, basically, is whether or not this quotient group is sensible, whether or not this quotient group has finite representations. So using representation theory, they can think about whether or not representation is finite, whether or not it's infinite, whether it's tame, whether it's wild, these sorts of ideas. So they're thinking about the singularities in string theory by looking at these quotient groups. So what I started to think about was, well, from my condensed matter perspective, is this useful for me? Is it useful perhaps for me to think about the algebra associated with these things? Now, if I'm a theoretical physicist and I'm thinking about a block vector, I can maybe think about a block vector via a stereographic projection. So I have a sphere, project it onto a plane. Now, if I go off and I talk to one of my condensed matter colleagues and say, what is a block vector? One of my experimental colleagues, they'll maybe show me a picture like this. So this is a picture, a photograph of what they would say the block vector look like in practice. So it's a set of chiral solitons defined along a nanowire. Okay, so it's a differential conductance profile. And basically each of these black walls is a soliton, each of the white walls is an anti-soliton. Okay? So they're defining the block vector with respect to that. Now the problem that they have, if I want to tell them something about solitons, anti-solitons, is I can go straight away and talk about the double-sided order model. I can think about this as a description for what's happening in functional analysis with solitons and anti-solitons. The problem, physically, if still thinking as a theoretical physicist, I look at this, I can see that the support is different between these soliton and anti-soliton states. There are a lot of them. The support isn't uniform. My theoretical physics understanding of this is pretty limited. I don't know what happens at infinity in this stereographic projection. I don't know what happens when I talk about the north pole and the south pole of this projection. Certainly when I start talking about varying the support, my understanding of what these singularities are, when I start having a large number of these block vectors that I'm somehow going to glue together, but I start physically rescaling the support of these things, somehow this gets even worse, a worse description of what these singularities are. So somehow I need something else. So basic idea of what I want to do.
Could you write closer to the top of the board? Because that's hidden.
Is that higher?
Could you possibly write on that one? Because
Yeah.
we're videoing and we can't see any of that. Thanks.
So the basic plan is I have some set of block vectors. Okay, and I want to talk about how to map the singularities so they have some sort of description. Now think of this purely from a physics perspective, purely from intuitively what we're going to get. Basically I'm going to get something like a polynomial ring. Okay? Our singularities, instead of being nice singularities defined on the ring, they're going to map onto a ring. Okay? So I want to talk first of all algebraically, how do I define that ring polynomial? And then do with the support? Is there anything I can say about the support generally which tells me a bit about the physics? Okay. So what I want to think about in the first instance is these polytopes. So I want to think about how I'm mapping these Riemann spheres onto some sort of space of points that I can talk about the analytic continuation properties. Okay. So this is an idea, you might have heard it before, might have heard it lots of times before, I don't know. It's an idea called toric variety. Okay. It's not that complicated, although it looks a bit complicated. So just pop back. Which one's back on? Okay, thanks. Right. So if I wanted to be fairly unambiguous about what I meant by the Riemann sphere, I really needed to start thinking about picking out infinities, picking out the points of difference. Suppose we want to talk about two of these Riemann spheres stuck together. I know I can make them, I know I can make these things by looking at ratios of complex numbers. And I know there are a certain number of ways that I can combine these complex numbers to make meaningful descriptions of this. This basically describes to me what a toric variety is. So what I'm looking at is I'm looking at a formal way of dragging one of these points across to here. Okay. How many different ways can I glue these things together? How many different ways can I describe that singularity? Okay. Can I pull it across in a 2D sense? Can I just have two 1D points joined together? So if you like the phase space, this state of all of these possible different ways of describing gluing together two of these singularities across the surface of the Riemann sphere is given by this toric variety. That's what it is. It's just the mapping. But in the quantum information language, what I want to think about with this thing is as a verifier. Okay? So I'm going to use this on some graph. I'm going to use these Riemann spheres as a vector space, find on some sort of graph, and then I'm going to use this as a verifier. So quiver is a graph with a directed graph. So I want to take something very simple, a square graph. I want to give it a bipartite tiling, perfect matching. I want to make some path algebra. Why do I want to do this? Because I want to think about braiding these paths. So I want to think about forming something like this by looking at the mutations of this group. So formally this is what how I would think about the algebra. It's not particularly important, I'm not going to do anything to it. So think about the algebra. Okay. So I can start to think about this in terms of gauge theory. I can start to think of this in terms of splitting this graph up into bits that I can analytically continue easily between these singularities and bits that I analytically continue onto some sort of sphere, onto some sort of ring that lives on one of these spheres.
5 minutes.
Yeah, yeah. I want to get to the book too. Okay. So this is how I'm going to write down my graph. I'll split it very simple-mindedly into two things. Okay. A bit that I can analytically continue quite easily between these singularities, and a bit that has a bit more information, a bit that has toric fit. This is the basic definition of meromorphic continuation. So if I have poles, I want to add another block sphere, I want to add another singularity, how does that in functional analysis sense, change the support. Okay? If I define an Allen transform to talk about the partition function of these states, how does that change the support? So this bound, this gives me a bound. Adding a simple pole, adding another pole, adding another block vector into the system, how does that change the definition? Well, it changes the definition in a prescribed way from meromorphic continuation, which is a bit like the Lee-Robinson bound, except it's not a planar limit, it's associated with the poles that I added explicitly. Why bother doing all this? Why bother setting up this construction? Well, basically, I have things that I can analytically continue easily. I have things that pick up a winding every time they travel around one of these singularities, one of these guys that lives on the sphere. This means basically that by construction, this thing is a Jones polynomial. This is a Jones polynomial in the integration graph. Okay. So I can implement this directly and look at this as a quantum simulator. So this is not a million miles away from something like quantum Monte Carlo. I have a stereographic projection of my Riemann sphere. And what I basically do is do something a bit like DMRG to construct an explicit Markov trace for these elements of the equivocation. If I want to recursively generate more and more values from these, so I want to somehow fill out the support. I can fill out the support from the Markov process. Rather than something box to box. I can then use ramification, simple linear algebra trick, in order to generate all possible values of this ring polynomial, in order to generate the coefficients of this ring polynomial. And then, another thing, so you get the Jones polynomial virtually for free, but the other thing is that the only possible way I can define the only possible way that this system can have a well-defined support is if I take the support associated with each of these Riemann spheres and then define a zeta function for it. So what it's telling me is I get something pretty much like the von Neumann entropy, which simply comes from the fact that I'm using a ring polynomial. And I have to analytically continue onto the ring rather than analytically continue to a single point. So this is the ring polynomial in practice. So this is the results of my numerics. These are the zeros of the ring polynomial. Okay? And using ideas about the support, basically these polynomial zeros pinch in onto the real axis, onto the real analytic continuation parameter axis, wherever I have some sort of bound or cutoff associated with the entropy. So the entropy separates into two, scaling of the entropy separates into two separate patterns of scaling. One's a definite non-analytic contribution, first order, because it's associated with the surface area of the Riemann sphere, the surface area that's non-analytic in the continuation space. And then the rest of it I can describe basically by a simple spin wave in my functional model. So those are the two items. This is the one from last week.
Okay, well, I think that brings us to the end of today's talks. Peter's of course happy to answer any questions that might arise en route to the pub or whilst playing football, possibly. So let's thank all of the speakers actually today for a very similar